Okay, let's unpack this.
Let's do it.
We spend so much of our time, focusing on technical skills, learning a new framework, or mastering some command line tool.
Right, the API of the day.
Exactly. But today, we're going to dive into something, I think, much deeper. We're talking about technical knowledge, specifically the essential library of writing that really shapes how the entire industry thinks.
That's right. And our mission for you, the listener, is not to force you to wade through like 50 obscure manuals or these dusty decade-old textbooks.
No.
We've done the sorting. We're basically extracting the key nuggets, the paradigm shifts, and the essential aha moments from a whole list of blogs and books and foundational papers.
And these are all curated and recommended by some of the most, insightful developers actually working in the field today.
Yeah.
So think of this as the ultimate shortcut to being truly well-informed. We're not aiming to give you just like surface-level summaries. We want to deliver the 2 or 3 concepts from these sources that genuinely change your cognitive framework, how you approach problem solving, regardless of what language or tech you're using today.
And what's really fascinating here is the sheer span of time these recommendations cover.
It's incredible.
The list goes from foundational classics written in the 1960s and 70s, by pioneers like Dijkstra and Liskov,
Right.
all the way up to these modern, hyper-specific discussions on GPU compute or like Rust memory safety.
So what does that tell you?
It fundamentally demonstrates a core truth, I think. Knowledge is most valuable when it's understood and applied, no matter how old it is. The core principles of high performance, clear abstraction, and robust architecture, they just endure.
Absolutely. We're talking about the evergreen ideas here. So whether you're prepping for a big architectural meeting, or you're just catching up on a field you haven't touched in a decade, or you're just curious about what makes the great minds tick, we're going to be extracting the core value from this amazing technical library.
Sounds good.
So let's jump right in with the pieces that really forced programmers to completely rethink how the hardware underneath actually works.
Okay.
I want to start with the mind-blowing stuff. The pieces that weren't just optimizations, but were truly revolutionary when they landed.
Yeah, the real game changers.
And for so many people in the graphics and high-performance world, that conversation really has to start with a concept that came out of the emulator community. Uber shaders?
Oh, the Dolphin emulator blog post. It's an absolute classic for a reason. When it first came out, people described reading it as just an absolutely mind-blowing solution to what seemed like an intractable problem.
Okay, but for anyone who hasn't dabbled in emulation or deep graphics pipeline work, why was it so mind-blowing? What was the actual problem they were trying to solve that required such a dramatic idea?
The problem was state explosion. It's just endemic to emulation. So to accurately emulate a console like the GameCube or the Wii, the emulator has to perfectly replicate the graphics processor's state machine. And game code is constantly switching these tiny rendering parameters, texture filtering modes, lighting setups, alpha blending rules.
Hundreds of times a frame, right?
Hundreds of times, even per object sometimes. And if the emulator tried to compile a new, unique shader every single time the state changed, you'd spend all your time just recompiling. It would lead to this horrible stuttering.
Okay, so that's the bottleneck. You can't compile a million tiny shaders on the fly. So what did the Uber shader approach actually propose?
They basically said, forget compiling lots of small shaders. Let's build one enormous comprehensive shader, the Uber shader, that encapsulates every possible combination of state we might need.
The whole game, or at least a big chunk of it.
A huge portion of it, yeah. And then they use conditional branching inside this massive shader to decide which path to execute based on the current state.
Wait, hold on. Wouldn't that result in a massive, inefficient piece of code? I mean, isn't that trading compilation complexity for runtime memory and inefficiency? That sounds like the opposite of optimization.
And that's the exact trade-off that made it feel like such a crazy idea at the time.
Right.
Uber shaders required a ton of GPU memory, and they increased initial load times dramatically. But, and this is the crucial insight, once it was loaded, the GPU could just execute this one complex shader continuously. The CPU didn't have to stop, reconfigure, recompile, and upload a new tiny shader every time.
So the bottleneck wasn't the GPU running the code, it was the communication between the CPU and the GPU.
That was it. The latency caused by that communication bottleneck was far more damaging to the user experience than the slight runtime inefficiency of running a large Uber shader.
And this is where it gets really interesting, connecting this sort of hack to the broader picture.
Yeah.
Because at the time, GPUs were just seen as these specialized graphics processors.
Exactly. Now, more and more general compute is being done on GPUs. You've got GPU compute shaders, modern APIs like Vulkan and DirectX
But
12.
it's standard now.
It feels standard. The idea of harnessing the massive parallel power of the GPU for non-rendering tasks, even if the individual instructions are a bit inefficient, is normal. But that shift, that mindset of pushing a huge, maybe wasteful but latency-reducing workload to the GPU, that's the historical importance of the Übershader. It was a pioneering look into maximizing parallel throughput over serial efficiency.
That is a fantastic example of a technique that starts as this clever hack to bypass a fundamental bottleneck and then ends up influencing modern architectural thought.
Yeah.
So moving from graphics compute to general high-performance architecture, we absolutely have to talk about the need for speed, and that's embodied in data-oriented design, or DoD.
Right. The book Data-Oriented Design is a must-read, for sure, especially for anyone serious about engineering, games, high-speed financial systems, that sort of thing. It's becoming more mainstream now, but the core takeaway is still missed a lot of the time.
Which leads to people not really getting the benefits.
Right. Exactly. It leads to inefficient adoption.
I think you hit on that crucial distinction. People get obsessed with the superficial techniques. Making sure their data structures are tightly packed or shifting from structures of arrays to arrays of structures. They focus on the layout.
And that focus is misplaced if it exists in isolation. It's a necessary step, sure, but the crucial point that gets overlooked is that DoD is not just about structure. It is fundamentally about maximizing throughput.
Okay, explain what you mean by throughput in this context, because I feel like that's the aha moment for a lot of people.
So throughput means optimizing the system to process the maximum amount of relevant data in the shortest amount of time. And the performance bottleneck in modern computing isn't the clock speed of the CPU.
It's the memory.
It's the latency of getting data from main memory into the tiny high-speed CPU caches. That's the whole game.
So when people optimize the layout, they're doing that to make the data fit better into the cache line, right?
Exactly. When the CPU fetches data, it pulls a chunk, usually 64 bytes, called a cache line. In traditional object-oriented programming, one object might have some relevant data, but also huge pointers or other state you don't need right now.
Wasted space.
Totally wasted cache space. DoD focuses on creating these flat sequential arrays of only the data you need for a specific operation. So when the CPU loads the cache line, that line is immediately filled with 64 bytes of purely relevant data that can be just blasted through the vector units. You maximize the usefulness of every single memory fetch.
So if I spend all my time rearranging my structures, but my processing loop is still jumping all over memory, or if it's full of if statements and complex logic inside that loop, I've gained almost nothing. I've optimized the layout, but completely killed the throughput.
Precisely. If you adopt DoD techniques, but don't focus on ensuring that your processing loop executes without stalls, on how the hardware actually uses the data sequentially, then you're missing the forest for the trees. DoD is a complete paradigm shift. It's moving from organizing code around abstract objects to organizing it around the physical constraints of the machine.
So it's about making the data flow like water through a pipe.
It's exactly that. Optimizing the pipe, not just the individual droplets.
That distinction layout versus throughput is absolutely critical. Sticking with graphics for just a moment longer, let's quickly touch on some of the great resources for newcomers, because that field changes so fast.
For sure. For new graphics programmers, two resources really stand out. The first is a more contemporary piece, Graphics Pipelines for Youngbloods.
And the audience for Youngbloods is specifically for those newer to the field, right? Like less than 3 years of experience, or maybe people catching up on the last decade of changes.
Exactly. The move toward physically based rendering, more complex geometry processing, it gives you context for the modern landscape. And it pairs really well with Reg's older but much deeper dive, A Trip Through the Graphics Pipeline.
Okay.
Reading both gives you the historical foundation, what pipelines looked like before DirectX 12 and the modern context, which is essential for understanding why modern APIs work the way they do.
And for just getting your hands dirty, the community highly recommends ray tracing in one weekend. People love that one for getting immediate, tangible results. I also saw a lot of praise for Amir Patel's Red Blob Games blog.
Oh, that's a phenomenal resource.
Oh.
Especially for algorithm visualization. The blog is known for its good interactive visual blog posts on algorithms for game development. It covers things like pathfinding, procedural generation.
The stuff that's hard to visualize in your head.
Exactly. When you're trying to really grok a complex search algorithm, Seeing it run interactively, watching the search space expand, or the path being calculated is so much more effective than reading pages of dense pseudocode. It hits that visual learning sweet spot.
So what you're saying is, if I try to synthesize this first section, the essential reading isn't just about learning new techniques. It's about adopting the mindset of high-performance architecture.
Yeah.
It's about optimizing for the actual constraints of the hardware, whether that's focusing on parallel compute to reduce latency, like with Uber shaders, or maximizing data throughput for cache efficiency, like with DoD.
Precisely. These writings teach you to think like an engineer who's trying to exploit the maximum potential of the physical machine, not just like a programmer writing abstract code. High performance is a dialogue with the hardware.
Okay, so we've established how to write fast code by talking to the hardware. Now let's pivot entirely to the human element. How we write reliable code and, maybe more importantly, how we interact with others about that code.
Right. This is where high performance becomes useless if the system is too complex to maintain.
Exactly. And many of the most useful articles in this library are less about pure zeros and ones and more about the social side and, I guess, the philosophical side of software architecture.
This section is full of essential philosophical clarity, the stuff that separates good engineering from just coding. Let's start with complexity management. When a large, old system gets complex, people's first instinct is often architectural surgery. They want to break it up.
And that's where Tef's post, How Do You Cut a Monolith in Half, comes in. It offers really practical, non-destructive guidance for that painful transition from one huge system to smaller services.
And it connects perfectly to another core thesis that everyone involved in microservices needs to, tattoo on their arm. Complexity has to live somewhere.
Yes.
This is the go-to article for challenging that often misguided notion that splitting something into 5 tiny components automatically results in simplicity.
That's the classic promise of the microservices evangelist, isn't it? We'll just break it up and all the problems will just vanish.
Right. But the reality is that complexity doesn't disappear. It just changes form and location. If you had a highly cohesive, complex business process inside a monolith, splitting it up doesn't remove the inherent complexity of that process.
No, it just introduces a whole new kind of complexity.
Distributed systems complexity, network latency, inter-service communication protocols, eventual consistency, complex monitoring. The complexity moves from inside one system, which you could debug in one code base, to this messy world of inter-system communication and coordination.
So what you're saying is, if I have a complicated flow, like processing an international financial transaction that involves currency conversion, fraud checks, regulatory reporting, that flow is still inherently complicated. It doesn't matter if it's one binary or 15 microservices.
Exactly. The article drives home that trying to chase complexity out of a system by fracturing it often makes the whole thing more complex. You've just added coordination overhead and network failure modes on top of the original business logic.
So good engineering is about managing complexity.
It's about managing it, not pretending it doesn't exist. You have to choose where the complexity should reside. And often, that distributed system complexity is way worse than the monolith complexity ever was.
That is a painful but necessary realization for a lot of developers. Shifting gears to team communication, a lot of friction and missed deadlines comes down to simple language choices, which is why the article just, the most dangerous word in software development, is so important.
The word just. It is so insidious. It's a classic example of minimizing, and it has these dual destructive effects. First, it minimizes complexity for the person speaking. We just need to update the database schema.
Right. And second, it minimizes the listener's perceived effort. Can you just quick fix this security vulnerability? I feel like I've been on both sides of that sentence, and it always leads to trouble.
Always. Because it sets completely unreasonable expectations. By implying a task is simple or trivial, you devalue the work of the person you're asking, and you set up a situation where any complication in software is full of complications results in a perceived failure.
Even if the task was incredibly complex from the start.
Right. Eliminating that one word from your technical vocabulary instantly improves clarity, transparency, and team respect. It forces you to actually articulate the real scope of the work.
That focus on clear articulation ties directly into another classic piece, how to ask questions the smart way. This has been around for decades, and it's still essential because we're constantly debugging and collaborating, and it directly addresses the notorious XY problem.
The XY problem is universal. It's not even just software. It's when a user or a colleague encounters a fundamental problem, let's call it X.
Okay.
But they try to solve it themselves first. They get stuck on their attempted solution, Y, and then they only ask you about why. They focus on how to implement their bad solution rather than explaining the original problem.
Which means if I only answer the question about why, I might give them a perfectly correct answer for why, but why doesn't solve X, so the actual problem is still there.
Exactly. The Smart Way article teaches you to provide the necessary context, list the steps you've already taken, and supply enough diagnostic info to allow the helper to properly diagnose the root issue, X.
It's not just about being polite.
No, it's an engineering principle. It prevents a massive waste of time on irrelevant solutions and quickly directs effort toward the core issue. It's the difference between asking, how do I use a hammer to install a light bulb, versus my light bulb won't turn on.
This focus on clear, written communication extends beyond just debugging. It applies to documentation and proposals, too. That's where writing well comes in. It's a guide on how to iteratively write good technical documents.
A lot of developers feel like their job is just coding, but they quickly realize they spend a huge amount of time writing emails, docs, PR descriptions, architectural proposals. And if their writing is sloppy, their code quality often suffers.
Right.
This guide helps developers get past the intimidation of writing. It gives them a practical methodology for producing clear, concise, technical documents that reflect the same precision as their code. It's about structuring your thoughts before you structure your functions.
We also see a really strong theme in this library about the balance between building for commercial value versus building for personal passion. It speaks directly to the open source and side project divide.
2 articles highlight this tension beautifully. The first is, an app can be a home-cooked meal. It's just a wonderful permission slip for the developer.
How so?
It reminds us that not everything we build needs to be commercially viable or scalable to millions of users. It can just be useful for you or your family or a small community. It validates the intrinsic joy of just building something.
And then you have the necessary pushback from the developer community with, I am not a supplier, which addresses the sense of entitlement that can sometimes plague open source.
That article tackles the often toxic dynamic where users feel entitled to the maintainer's time, bug fixes, or feature requests just because the code is available.
Right. I found your code on GitHub. You now work for me.
Basically. The core idea is simple. Just because you put code out there, it doesn't create a contractual 247 obligation to every user. It's crucial for setting boundaries and managing expectations and just preserving the mental health of independent contributors. You're offering a gift, not a service-level agreement.
Finally, let's talk technical debt, the eternal anxiety-inducing debate. For years, the wisdom was to demand these separate, big engineering projects, the mythical tech debt sprint, just to tackle it.
And that brings us to don't fix it just because it's technical debt. This piece was revolutionary because it shifted thinking away from that approach. It recognized that those debt sprints rarely happen, and when they do, they often introduce new, unrelated problems.
So how did it change the approach? What was the new framework?
It introduced the idea of technical debt as an option, not a moral failing. The goal isn't to eliminate all debt, it's to manage the interest payments. If you haven't touched a 20-year-old piece of code in 3 years and works perfectly, its debt is effectively irrelevant.
So you don't pay?
You don't. The article encouraged the practice of bundling debt remediation in with feature development. If you are touching a system to add a new feature, that is the optimal time to clean up the debt in that specific area. You're already there, you have the context.
So you pay down the debt when you're already making a withdrawal. It focuses the cleanup effort exactly where the system is currently under stress.
Exactly. It ensures you're investing in the most actively used parts of the code base. It's an enormous practical takeaway for management and individual contributors alike.
Okay, let's transition now from the philosophy of how we organize and talk about software to the languages themselves and how modern paradigms are encouraging these radically different, safer ways of programming.
Right. And when we talk about modern safety paradigms, you have to start with Rust. It has fundamentally redefined the conversation around low-level safety without needing a garbage collector. For anyone who needs to bridge that gap between high-level application programming and low-level concurrency, understanding memory ordering and synchronization, the book Rust Atomics and Locks is essential. One commentator called it definitely the best technical book I have read in a long while.
So why does it stand out so much? There are a lot of good resources out there.
Because it tackles the intricacies of safe, concurrent programming head-on. Most of us operate in an environment where memory ordering is just handled for us, by the language or the hardware. But when you get into the guts of operating systems or high-speed data structures, You have to deal with things like atomic operations and memory fences.
Or really scary stuff.
The really scary stuff. This book doesn't just explain what Rust's primitives are. It dives deep into the why. It explains memory models and cache coherence in a way that is incredibly clear and practical. It shows you exactly how Rust enforces its safety guarantees, even in highly concurrent code.
So it teaches you how to use those unsafe blocks with a full understanding of the hardware implications.
Precisely. And you also see mention of Brown's Rust book experiment as another high-quality resource, which reinforces the idea that the best writing about Rust is focused on these deep, foundational concepts, not just the syntax.
That focus on explicit, detailed safety leads us pretty naturally into powerful, functional programming concepts, even if you never write a line of Haskell. Alexis King's writing, specifically the post parse don't validate, is a huge favorite in this library.
It is a phenomenal piece, and it's cited as a favorite because, for many readers, it literally changed how I think about programming.
Wow.
The core insight tackles this really common problem, dealing with messy external input like user forms or JSON data.
Right. And the traditional approach is to just accept the data as a generic string or object, and then you write a bunch of validation code, if statements, boundary checks, regexes, to see if the data conforms to what you expect.
Correct. And that validation code is always prone to error, especially if you have to validate the same piece of data in multiple places across the system.
It gets messy fast.
The parse don't validate principle flips this completely. Instead of accepting unstructured data and running tedious checks, you structure your code to parse that input into a custom data type that is guaranteed by construction to be valid.
Wait, okay, let me make sure I understand the conceptual distinction. If I need a valid email address, instead of accepting a string and then running a valid email function everywhere, I create a new data type called, like, valid email address that can only be created if a parsing function succeeds.
Exactly. If the parsing function fails, you get an error. You never, ever get an invalid instance of valid email address. It's a powerful application of algebraic data types. You shift the burden from thousands of risky runtime checks to one single, robust parsing function and the type system. Once you have an instance of that valid type, you've eliminated an entire class of potential bugs downstream.
It makes illegal states unrepresentable.
That's the mantra. And critically, Alexis King's writing has this distinct, engaging personality that makes these concepts really accessible, which is why it's so beloved.
You also see high praise for real-world OCaml, which really underscores that functional languages are moving beyond academia and into practical industrial use for things like static analysis and compiler tooling.
Yeah.
But maybe the most intriguing deep dive here concerns the very foundation of systems programming, the C language.
Yes, the article C isn't a programming language anymore is fascinating because it forces you to confront the astonishing assumptions that underpin so much of the modern computing world.
So we're not talking about the syntax of C, which is famously small and simple. We're talking about the environment C operates in.
Precisely. The article dives into the historical baggage and the deep, often unstated assumptions baked into the C linking model and how we interact with objects and libraries at that foundational level. We often forget that the C standard, the actual document defining the language, is often divorced from what the compiler and the operating system actually do.
So if C isn't just a programming language, what is it?
It suggests C is less a traditional programming language and more a lingua franca, a common assembly layer that's built on historical conventions that modern compilers and operating systems just assume. The article highlights that the true complexity isn't in C syntax, but in the environment, the accumulated design decisions, and the unspoken agreements about memory layout and calling conventions that have been layered on top of it for decades.
Wait, can you give me a concrete example of one of these astounding assumptions?
Okay, think about something like data alignment. The C standard might give the compiler some latitude, but in practice, millions of lines of C code rely on very specific architectural assumptions about how the linker resolves symbols, how data is aligned in memory, and how functions are called across libraries. These are assumptions that are enforced by the environment, not necessarily guaranteed by the C spec itself.
So modern C programming is actually about managing this mountain of historical context.
Exactly. It's far more complex than learning the for loop syntax. It makes you appreciate the complexity lurking beneath a seemingly simple #include statement.
That's a wonderful reminder that what seems like a stable foundation is actually this mountain of agreed-upon compromises and history that we just take for granted every time we compile a binary, which takes us perfectly into the texts that define how software is built in the first place.
Right. How computers read our intentions, from parsing input to fundamental structure.
Let's start with the tools that build the tools, parsing and compiler design.
For anyone who has struggled to write a robust, resilient parser, which is a task that sounds simple but gets messy, FastMatCloud's work is just indispensable. The post's Simple but Powerful Prat Parsing and Resilient LL Parsing tutorial are highly cited and revered.
One fan even noted they go back to those specific articles a lot when writing parsers. Why is Prat parsing so powerful compared to, say, a simpler recursive descent approach?
Prat parsing is this elegant, expression-based technique that dramatically simplifies handling operator precedence and associativity. If you're parsing something like 3 plus 4, 5, a standard recursive descent parser needs complex logic to handle the fact that multiplication binds tighter than addition.
Right, you get a lot of nested function calls.
A ton. Prat parsing uses a simple, unified mechanism of binding power that applies to all tokens. It lets you write a clean, concise, and incredibly robust parser for complex expressions without drowning in specialized functions for every precedence level.
And what about the resilient part of the second tutorial?
That's crucial for modern developer tooling. A resilient parser is one that doesn't just crash when it sees a syntax error. It's designed to recover, maybe skip the bad token, and keep parsing the rest of the file. This is essential for features like auto-completion and syntax highlighting in modern IDEs. MatCloud's work provides practical blueprints for building tools that are helpful even when the code is temporarily broken.
Moving from parsing the source code to optimizing the runtime, we have two essential references for internal compiler design.
Those would be speculation in JavaScript core, which is a foundational text in JIT just-in-time compiler design. It details how modern execution engines predict behavior to maximize speed. And then there's how I implement SSA form.
SSA static single assignment. It's one of those theoretical concepts that sounds incredibly dry, but underpins almost every single high-performance compiler today. What does that article offer?
Well, SSA is a practical requirement for so many powerful optimizations. It basically ensures that every variable is assigned a value only once. If a variable is reassigned, it's treated as a new variable, like by 1, by 2, by 3.
Okay.
This transformation makes the data flow explicit and trivial for the compiler to analyze. How I implement SSA form is an essential practical reference because it moves beyond the theory and gives you the concrete steps needed to actually implement this crucial intermediate representation in a modern compiler.
And that allows the compiler to easily figure out when a value can be eliminated, dead code elimination, which is the foundation of modern high-speed execution.
Precisely. If you want to understand the magic happening under the hood, these are the sources that explain it.
This discussion leads us naturally into the golden age of computer science. The mid-century pioneers who were literally defining how we structure code before modern languages even existed. The structured programming debate defined the early 1970s.
Oh, yeah? We see the foundational works. Dijkstra's seminal notes on structured programming and Wirth's program development by stepwise refinement. These works argued passionately for reducing complexity, controlling flow, and using clear, logical structure.
And what was at stake here? Why the absolute insistence on moving away from things like the GOTO statement?
The stakes were reliability and correctness. In the early days, code was a tangled mess spaghetti code, which relied on GOTO statements jumping all over the program arbitrarily. This made the program's flow impossible to reason about. Dijkstra famously argued that the quality of programmers was an inverse function of the density of their GOTO statements.
Because it just introduced too many possibilities.
Too many possibilities. The goal was to reduce flow control down to predictable, simple structures like if-else and while loops, whose correctness could potentially be proven mathematically.
And then, providing the critical counterpoint, or at least the necessary nuance, you have Knuth's structured programming with a go-to statements.
Knuth's piece is required reading precisely because it offers this mid-70s view from someone who understood performance at a deep machine level. He used assembly language as a pedagogical pseudocode, showcasing the hard version of what Dijkstra others were arguing against. He showed that GOTOs, if used judiciously, could result in performance gains in highly optimized tight loops.
And the famous quote where he justifies using GOTO is so often pulled out of context.
That's the lesson. Knuth's careful nuance that GOTO might be acceptable for optimizing a tiny, highly performance-critical kernel of code is often lost when people try to use his comments to justify their poorly organized spaghetti-style procedural code. It's a great lesson in reading the original source material.
Beyond flow control, abstraction was the other great frontier. Liskov's abstraction mechanisms in CLU is noted here as a very forward-looking work.
What's fascinating about Liskov's early work on the CLU language is the irony. Liskov is well known today for the Liskov substitution principle, which deals directly with inheritance and subtyping. Yet her earlier work on CLU actually eschewed inheritance entirely.
She rejected inheritance. What was the alternative form of abstraction she was championing?
CLU focused heavily on data abstraction and generic programming. It introduced the concept of the abstract data type, or ADT, which bundles data and the operations on that data, defining a public interface while hiding the implementation details. She prioritized strong encapsulation over the flexible but sometimes confusing relationships introduced by inheritance.
So it was an early path for object-oriented thinking that was different from what we ended up with.
A path focused on pure encapsulation and parameterized types, yeah. C++ and Java later largely marginalized that in favor of inheritance hierarchies.
And anchoring the theoretical base for all of this, you have Strachey's Fundamental Concepts in Programming Languages, which is foundational for articulating many programming language theory, or PLT ideas, for the first time.
That work is a beautiful snapshot of the time when computer science was just starting to get a grip on PLT. Before this, concepts were often just implicitly defined by the language implementation. Strachey provided the clear articulation for concepts like the distinction between L values and R values, or even aspects of scoping and semantics.
The stuff we now teach in CS 101,
but which were revolutionary articulations at the time.
We can't conclude this section on foundations without mentioning the evergreens, the books that are on every programmer's bookshelf, even if they haven't been cracked open in a decade.
That category has to include the C programming language, K&R, which is often the first true systems programming book a developer encounters. It's concise, elegant, and ruthless.
There's also the Perl programming language and, maybe most universally, the pragmatic programmer.
They persist because they offer more than just syntax. The pragmatic programmer especially is full of this philosophical generalized advice. They serve as reminders of pivotal times in a developer's education. They taught timeless principles, from the importance of clear code in K&R to the advice in the pragmatic programmer about fighting software entropy and taking ownership of your work.
They're professional touchstones.
Exactly. They transcend language versions.
Okay, so now we move into the final category. The articles and books that provide these specific, deep, yet accessible explanations, the ones that offer a unique insight or are just masterclasses in technical teaching.
Right, the curated gems.
I love this first one because it's something everyone has encountered, usually in a moment of frustration. Why is this piece of hardware so much more expensive than the last version? Specifically, the dive into USB 3, why it's a bit harder than USB 2.
This is a favorite because it explains a consumer observable market phenomenon, the price increase of USB 3 hardware when it launched. And it does so on several different levels for readers, with different levels of background knowledge. It's a masterclass in teaching real-world signal integrity.
So what's the engineering complexity that justifies that price jump?
It's the speed. USB 2 runs at 480 megabits per second. USB 3 introduced super speed, which runs at 5 gigabits per second. That massive jump in frequency introduces fundamental physics challenges.
It's not just make the numbers go up.
Not at all. For a beginner, the article explains concepts like crosstalk and electromagnetic interference. For a seasoned engineer, it dives into the complexities of high-frequency signaling, the need for precise impedance matching, the difficulties of running two full duplex differential pairs simultaneously, and the expense of the shielding and precision engineering needed in the cables and connectors.
So a USB 2 cable can be relatively sloppy and still work because the signal is slow and forgiving. But a USB 3 cable requires incredible precision to prevent the signal from corrupting itself.
Exactly. It demystifies a piece of commodity hardware and shows the significant engineering complexity hidden inside. It's a great lesson that abstract data rates always have concrete, physical, and monetary consequences.
Shifting to the practical and clever, we have some great insights on shipping quickly and applying high-level tech to fun, almost silly projects.
The development notes from XKSlow's machine are great for anyone building something for a hackathon or a small utility. They offer insights on shipping a silly thing fast and making it run practically, often leaning on simple hacks like using image recognition instead of deep API integration.
It's a celebration of the minimum viable product.
Totally. And then there's the competitive spirit in the project, achieving first place in Tetris 99 using computer vision, classical AI, and a whole lot of free time.
I'm so intrigued by that one.
It's a wonderful example of combining complex fields, computer vision to read the screen, classical AI for planning the next move, and then amazing hardware hacks to interact with the controller. It's inspiring because it shows high-level expertise applied to a fun, tangible, and highly competitive goal.
And speaking of AI, we have a couple of explicit mentions here. One is a great example of explaining a foundational shift, NLP almost, from scratch.
That article is noted for doing a great job of describing the why should I care and the what for what was, at the time, a new paradigm in natural language processing. It successfully breaks down complex concepts, showing how the field was moving away from brittle, rule-based systems towards statistical models and deep learning.
It showed the audience why that shift was necessary and what benefits it unlocked.
Exactly.
We also have two highly recommended books that serve as excellent conceptual introductions to computing and secrecy, not technical manuals, but deep context providers.
Code, The Hidden Language of Computer Hardware and Software, is cited as an excellent book, often a favorite gift. It beautifully connects the abstract world of software, the ones and zeros, down to the physical realm of switches and logic gates and wires. It demystifies the whole stack.
And then there's Simon Singh's The Code Book.
The Code Book, The Science of Secrecy from Ancient Egypt to Quantum Cryptography. That one was loved for its broad sweep across history. It brings the topic of data integrity and protection to life through human history. It connects historical ciphers to modern cryptography, which gives you crucial context for today's digital security.
And finally, let's acknowledge that not all essential technical writing is serious. There's a lasting appeal to writing laced with humor and snark, often born from shared frustration.
Oh, absolutely. The technical world thrives on self-deprecation. This category offers essential cultural touchstones. You see the enduring power of pieces like Programming Sucks, or The Night Watch, or the visual gags of Watt.
The talk explaining Watt turning Watt into Y is also fantastic.
They make you feel seen when you're struggling with some bizarre language quirk.
And you can't forget the truly legendary technical snark, which is parsing HTML rejects, aka Zalgo-Hicams.
Oh, that article is perfect. It's a perfect blend of high technical detail, explaining why regular expressions cannot handle the recursive, context-free grammar of HTML and pure existential dread delivered through humor. It truly encapsulates the idea that the best writing is memorable, whether it changes your perspective on object orientation or just makes you laugh at the impossibility of the task.
That was an incredible, wide-ranging tour. We successfully tore through foundational computer science classics from the 70s, high-performance architecture breakthroughs like Uber shaders and data-oriented design.
Modern language paradigms like Rust and Parse don't validate, crucial architectural soft skills like managing complexity and tech debt.
And some truly witty commentary on the inherent difficulty of the craft.
It was a serious deep dive. And the sheer breadth of sources, covering over 50 years of computing, is really the main takeaway. We focused on the sources that don't just teach you how to code, but how to think like an engineer.
Right.
Whether it was the insight that complexity just shifts location when you go to microservices, or the realization that performance is a function of throughput, not just data layout, or the need for clear communication from how to ask questions the smart way, these pieces provide the mental framework for true engineering excellence.
So if we connect this to the bigger picture, what really stands out is that the best technical writing doesn't just explain what happens or how an algorithm works. It actually changes how you approach the underlying principles and challenges your default assumptions.
It forces a cognitive shift.
Exactly.
It does. It shows you there are paths not taken, like Liskov showing that abstraction doesn't require inheritance, or that there are fundamental unavoidable laws of physics governing things like signal integrity in a simple USB cable. The core lessons are timeless because they address human cognitive limitations and physical hardware constraints.
And now a final provocative thought for you to chew on as you go about your week. We mentioned that the codebook was loved, but one commentator wished for a second edition to update its final chapters. Given the explosive, rapid evolution of fields like large language models, modern cryptography, and high-performance accelerator architectures in just the last 5 years, what foundational technical text from that period do you think is already due for a major second edition?
Ooh, that's a good one.
Which essential book is already having its last chapters rendered obsolete by the sheer speed of progress? Something for you to mull or explore on your own.
That's a powerful question. Given how fast the ground is moving beneath our feet, the shelf life of knowledge is getting shorter and shorter.
Until next time, keep digging into the sources.